Hi, welcome to my talk, Embedded Rust on IoT Devices. My name is Lars Gregori. I'm working at SAP Hybris in Munich, and there I'm working at the Hybris Labs team. And at the Hybris Labs team, we are building prototypes. We're connecting Internet of Things with our e-commerce platform. And here you can see on the left side our smart wine shelf. For the blinking and lift up of the wine bottles, we're using Arduino, and for the communication, Raspberry Pi. In the middle, we are using a light blue bean for the BLE communication, and there's also an Atmel processor on it, same as an Arduino. And on the right side, it's our infinite card prototype, which uses an ESP8266. So we are playing around with embedded devices. And the motivation for this talk was this page I found. It was about functional IoT. And on this page, there were 3 programming languages and also Rust. And I thought, okay, Rust is something functional. Maybe you have to look at it. A friend of mine told me, yeah, you have to look at Rust. I thought, okay, maybe that's the starting point. But there also was something interesting on this page with imagine how IoT devices are. So they are connected to the internet. I mean, that's the point, Internet of Things. Without internet, they are only things. They developed in short time, storing personal data and also sometimes a Wi-Fi password. So therefore, they have to be secure. And they're getting more intelligent and powerful. But on the other side, cheaper. And also with the service and all the old code, which is maybe not updated, that's all the problems we are getting now, starting every day. You're reading on the news, some botnet is up, and the Zigbee protocol for the Philips Hue or something was hackable. And the page asks, can C be designed for the Internet of Things like this, for the devices? And the answer was, no, it can't. I thought, okay, maybe I have to look more into Rust. So my talk will be about giving an overview about Rust, looking at embedded Rust, cross-compiling, and microcontroller debugging. Yeah. So let's start with an overview. When you go to rustlang.org, you can install it and download it. And there's also some information what Rust is. So Rust is a system programming language. It's fast, it prevents segmentation faults, that's the main problem with the C++ language, and guarantees thread safety. Okay, so I looked at the FAQ page. Yeah, safe, concurrent, practical system language, nice. But there's also one sentence. They don't want to be 100% static, safe, or reflective, not too dogmatic. So for example, if you have unsafe code, you mark this code as unsafe and don't get the help of the compiler, but you can use unsafe code if you want. And Rust is developed by Mozilla for their next browser engine called Servo. And they already take some parts of this proof of concept and put them into the Firefox. So in the actual Firefox, you already have some Rust code. And Rust is multi-paradigm, so it's not only functional programming, as I thought in the beginning, it has also some OOP code paradigm inside of it. But the interesting part is don't use a garbage collector. So with the intelligent memory handling, they don't need a garbage collector. And it's built on LLVM. And Rust is cross-platform, so you can use it on Android, iOS, and yeah, that's the talk here about embedded devices. And you have the conditional compilation, so if you have some code, especially for a Mac or for some embedded device, you can mark this code. But what makes Rust so different? This is the control and safety. So if you look at some Rust videos, you get an overview with the control. This is how you can access the memory. So with C++, you can access every part of a memory. But on the other side, you're not safety. So the language itself doesn't help you really to access parts which shouldn't be accessed because you have something wrong in your code. And then you go down with Go, Java, Python, and at the end you have Haskell, which is totally safety, but you don't have really control about it. So the question is, where's Rust in this diagram? There's a gap between C, C++, Go maybe? No. It's totally you have total control about it, and it's absolute safety. And when I thought this, I thought, okay, let's get more into Rust. And the reason for this is the Rust concepts. So the key concept is the ownership. And then we have borrowing and references, and the lifetime, which is an advanced concept of the borrowing. So I will show you now some ownership and borrowing code examples. I skipped the lifetime because, when you play around with Rust, there's this nice sentence in the documentation where you can find here, you have to fight the borrow checker. So you get error messages and think, why is this happening? And then you have to think about, and it's like a gamification. It's like you try to fix it, to let it run, and at the end, you get more and more into the borrow checker. So here we have the ownership. I have a vector 1, 2, 3. In Rust, Rust uses a macro for this. That's the reason with the exclamation mark. Then we assign this vector to a second variable, do something, and at the end we want to print the first element of our vector. So what will happen? You get an error. Use of a moved value. So when you assign your first vector to a second variable, you also move the ownership. And the reason for this is there could be something inside of it, like take something out of vector 2. So you don't know if your first element exists, which value it will have, or something like that. Here I have an example. I have value 1, assign it to v2, and print it. In this case, everything is fine. The reason for this is integer and primitive types are using a copy type trait. So every time you assign a value to another value, the value will be copied. And the vector itself doesn't have this. One of the reasons maybe if someone wants to copy 1 million items from one side to the other side and around, it gets slow. You can implement your own vector with a copy type of it, or you can use this kind of code. So in Rust, you define a function with the fn keyword. Then we have the function name. Then the parameter with the type of the parameter. In this case, we are having a vector with a 32-bit integer, a second parameter, and after the arrow, you have the return type. In this case, we have the two vectors and also an integer 32-bit. Then we do some stuff with vector 1 and 2, and hand back the ownership in our return type with vector 1, vector 2, and 42. So in this case, we are defining some vectors, calling the function, and get back the ownership. But it looks a bit complicated to write this kind of code, so there's the possibility with references. So here you can see the vector has an ampersand now in front of it for reference, and we only have to return one type. So we can do the stuff, return 42 as answer, and when you call the function, you also put the ampersand as a reference for these values and can use it. I think that's clear. But what happens if you want to change something? So in this case, we're having a vector and put vector value 5 on it. And here we're getting an error once again. But this time it cannot borrow immutable borrowed content as mutable. I mean, you have to think twice and you get it, okay. I borrowed this as immutable, so I'm not allowed to change it, but I want to change it. The reason for this, every variable in Rust is per default immutable. You couldn't change it. So if you want to change it, you have to use the mutable keyword. So in this case, we define x as a mutable variable. Then we assign y with mutable reference to x, add to the value 1, and at the end we want to print it. So what will happen? Everything is fine. 5 plus 1 is 6. The reason for this is first the mutable and the curly braces. So in this case, the code gets a different scope, moves scope in, and after the end, scope destroys everything inside it and giving back the reference. It's the same if you would call a function. I can see some faces with getting more, getting complicated. So the rules for borrowing. First, you have a scope which have to be less or equal than your main scope. And the other rule is you have only one or more references in this type it's immutable, or exactly one mutable reference, but not both of them. So what happens if you take the curly braces away? We're getting an error once again. And this time, you're getting an error because you cannot borrow an immutable variable also as mutable. So on the top we have the mutable and want to read it immutable. And this is against the rule where you only have a mutable or immutable variable. So at this point I think you get an idea but not understand it completely. So you have to play around. On the document page, there are runnable examples in the browser. You click on it and can remove the curly braces or something, and then you get an error and play around, and after half a day you get it a little bit more clear. Okay, now going to the embedded Rust part. I found a project on GitHub. It's Sync. It's an experimental project at the moment. It's for the ARM processor. It shows Rust best safety features. It's mostly assembler-free and completely C-free. For this example, I'm using an STM32 Nucleo F4, which you can see here. Can everyone see it? Yeah, I think. Oh yeah, here we are. So in the middle, the black dot, that's the STM F411RE. Then we have left and right some sockets, also an Arduino compatible socket, some LED, it's already on it, some buttons, and a USB connection for it. And for this example, I'm using the green LED already, so PA5, just remember A5, and PC7, C7. This is where I use for this example. So let's take a look at the demo. Oh, enough space, great. Make it a little bit bigger. So these are the examples which the Sync project already have. So we have, most of them are Blink examples. There's a Bluetooth low energy example and some serial communication. But I'm staying on the Blink example. So in this case we have source main. I think everyone can see it, yeah. So in the first line we're using feature. This means inside of Rust is every day new developed or continuously developed. So on a nightly build, you can use the feature keyword. On a stable build, they're not allowed. So for this example, I need a special version, a nightly build version. So the idea behind this is you have some new features, you put it in a nightly build or in beta version, and if they're successful, they go into a stable version. Then we have the no standard keyword. This is for embedded devices. It's not using the standard C library. We don't have file access or something, so we just skip this. Then here's the part how to import something into Rust. It's a little bit different than in Java, but I think, yeah, you can also make it big. Then we have our main function. In this case, we have to initialize the stack and also the data, because we are embedded. It's also the same if we do some assembler programming. But if you do Java, it's there, so you don't have to think about. Then we have our LED, our first one. So here I'm using port A and pin 5. So this is A5. This case is an unsigned 8-bit integer as an output. Then I have LED 2, C7 in this case. Set up the LED, set up a timer, define a variable for the delay, and here I have the loop. Set first LED on, second off, wait, and the other way around, and wait again, and loop through it. Okay, cross-compiling. So if you download the Rust compiler, from the internet, from the Rust page, you have the stable version. But if you need some nightly builds or something, you can use Rust Up. It's an installer for Rust. And then you just say install nightly something from September. Then go into my Rust project and override the default setting. So every time I go into this directory, I'm using the nightly version, and outside I'm having a stable version. Then we also need some GNU compiler for this, for the ARM version. So here you can see ARM. We are on the ARM processor. None means it's bare metal, it's no Linux or something running around on it. And it's an embedded application binary interface. That's the EAEB. Rust is using Cargo as package manager. With Rust build, we can build it, and I just put here the target and feature parameters on. They also can put into some configuration, but to make it more clear, so we are using Thumb v7. It's some ARM code base, and the features of the STM32F4. Okay. So let's go out. Here I have my build file with this, all of them, run it, and it's already done because I already compiled it. If you compile it from scratch, it will take a little bit longer. So now I've changed some value because you can already see it's blinking. I changed the delay to 100. Build it. Takes a little bit longer. And now I upload it. It always fails. That's cool. And now it's blinking faster. So with the upload, I connect the Nucleo board to my laptop, and it's getting as this storage device, and just copy the binary to the storage on this. I can show it here. You can see it on the last line, maybe a little bit higher. So copy, let's call it, text. Copy it to the volume node F411RE. Okay. So, and as you can see, it's blinking faster now. So I really changed the code. It's really Rust. It's not some default example or something. Okay. And now I will debug on it. So there's some error, some failure already inside of the sync project. You have to comment out the debug GB script thing, and then you can build compilable, debuggable code for it. Otherwise, with release code, it's no problem with, yeah. And for the debugging, I'm using OpenOCD. So this connects to the microcontroller and open up the port 3333. And then I can open the debugger, connect to it remotely on this port, load the file, and then I can do something. So I will do it now. First of all, I start the OpenOCD. As you can see, the microcontroller stopped now. And there's lots of flashing here, so there's serial communication with this device. Then I open up the debugger. Target, remote, 1300. Then I need this file. Just copy it. I want to overwrite it, yeah, no problem. And now I can list my Rust code, so you can see it here. I can also set a breakpoint and the main function. This is somewhere here at 11. And I want also a breakpoint at 32. That's the first time I'm setting the LED 1 to high. Now I can continue, and it stops at main. I can now type next to go further, and it stops on line 34 with set high. So I just continue once more, and then you should see the LED blinks and stops again at 34. And now I can step into it. So this is the function itself, set high. Then I get the offset, it's the pin number. I can also print self. So that's a reference. I print self pin. It's number 5. Do I already have the port? No, I think not. Step further. And that's the off. No, that's the offset through. Where do I get a port? There's somewhere the port. Ah, it's on the get registered. So here you can see the BSRR. It's some memory on the device, and with changing the flag to true, I'm setting the output to a high. And that's when the LED turns on. Okay, I just continue now, because now I can also show the variable delay 100. Just change, I can also change it, set delay to, I do it 1 second. So, and when I now continue, it takes 1 second and should, no, it was too fast. Continue. I'm having, okay, oh yeah, thank you. Set, delay, have to look what's, I always forget it. Why do I need a equal sign? Okay, now it takes longer, yeah? Break. 1, 2, yeah. So I also can change the variable. I can also disassemble this code. And I always I'd copy it. I couldn't write disassemble. This is ARM code. Looks like a little bit like Java bytecode. And when I go to 600 somewhere, here we are. With the arrow in front of it, then you can see a BL, that's a branch load, so it's a call to our set high function. I think that's, yeah, continue, break, file, everything. Demo I've already gave. So what have we seen today? A Rust overview, embedded Rust code, some Rust code also, how to cross-compile and debug it. What we didn't saw was the hello world, the typical hello world, but the blinking hello world for embedded devices. Yeah, that's it. Some question, I think there. I couldn't answer borrow checkers questions in the short time, so.
I guess Rust is generating C code because you need the C compiler. Would it also run on an ESP8266?
Should run. If you have the compiler for it, they don't transfer it into C code. It's wow, good question.
Because I saw you needed the C compiler, so I thought.
Yeah, it's a C that's the ARM compiler. Yeah, right. I'm not sure if they're using a C code on it. That's a good question. Yeah, didn't look at it. What they're really doing in the back end on it. Some other? Yeah. At the moment, it's only they started this project and continually developing on it. And at the moment, there's no Wi-Fi connection or something. So this is, yeah, I think it's also something which will be more complicated to rewrite everything into Rust. So this is also one main problem with Rust. There are lots of C code, lots of libraries outside of it, so you can use it with Rust. But in this case, you are using the unsafe part, and yeah, then you still have the problem that this library will have some problems, and everything will be unsafe. Yeah. More questions? I'm around. Yeah.
What is the minimum system requirement? How small can the microcontroller be? How many?
Oh, that's a good thing. There's an STM-L1 also, which this is the F4. It's a little bit more powerful, but it doesn't have to be powerful. This one has 512 kilobyte flash and 128 kilobyte SRAM. We're talking about kilo, not tera or something. Yeah, and the L1 is also possible, and I have it here somewhere. Okay. More questions? Thank you.